All right, before I do get into dilations, first thing I want to talk, new vocabulary term up there, invariant points. Invariant points. Those are points that do not change. Points that do not change after a transformation. Okay, they do not change after a transformation. So I have point A, I perform a transformation, and A prime is in the exact same place A was. Some type of transformation did not change it. So I have a quadrilateral up here, number one, that says, hey, here's A, here's B, here's C, here's D. I don't want you to graph it. There's no need to graph. So I'm going to start with point B. Point B is 0, -3. So up on I'm going to do a quick sketch for you here. 0, 1, 2, 3. Here's point B in quadrilateral ABCD. What I need your help with is, can you come up with a transformation, and be specific, that will land B prime exactly where B is? So B is not going to move after I perform your transformation. That would make it invariant. Can we come up with a specific transformation that I apply to point B and it's not going to go anywhere? That would make point B invariant. Kyla, go ahead.
A rotation around point B.
Okay, I could do a rotation of any degrees around point B. Point B is not going anywhere. There's one. Yep, Maeve. Okay, that's good too. I'll write that one. Reflection over the y-axis. Everyone agrees if I reflect over the y-axis, B is not going anywhere. All right, I'm going to challenge you, honors kids. Somebody give me another reflection over another line where B would not go anywhere. Sean?
Y equals -3.
A horizontal line, which we know starts out with y equals, and in this case, -3. Correct. That horizontal line going through B would not move B anywhere, right, guys? All good there? Now, look, I don't want to get silly here. A rotation to 360, translation is 0, 0, or we're better than that, right? We're better than that. Okay, but that would make point B invariant. It does not move. All right, what about point D now? Point D is 3, 0. 1, 2, 3. 3, 0. Can you come up with a couple transformations that would make D invariant? Quincy and then Hannah.
A reflection over the x.
There you go. Now I can do a reflection over the x-axis. Did he take yours, Hannah? Okay, go ahead.
A reflection of y equals 3.
Yep. X equals 3. Good. A reflection over the vertical line, x equals 3. Perfect. Good job, guys. Good job. Okay, so that's invariant points. Points that don't move at all after a transformation. Questions there? Comments? All right, now let's hit up dilations. Because I say the word dilation, and then you guys probably in return give me 2 words. Enlargement, reduction, right? Bigger or smaller. That's probably what you guys think about with dilation. I need to change that thought process today. Because yes, that's what happens to a figure when you dilate it. It gets bigger or smaller. But I hate to break it to you, when you dilate a point, it doesn't get physically bigger or physically smaller, okay? So what happens to a point when you actually dilate it? Let's talk here. Go ahead. I'll give you guys a couple seconds. On number 2, plot triangle ABC for me so we can talk what actually happens when I perform a dilation. So everyone at home, go ahead, plot triangle ABC. All right, let's talk now. So part A says graph and state the coordinates of the prime after an image when I dilate by 2. All right, first thing, notation. Every single transformation we have done so far has notation. Reflection, lowercase l. Translations had 3 different notations. Rotation had capital R. Dilation, capital D, with a subscript of what you're dilating by. So in this case, the subscript would be 2. That 2 has a name. We've actually used this term when we did similar triangles. That 2 there is what's referred to as the scale factor. It's basically the ratio of the original to my image. And a reminder, here you go. If the scale factor, I'm just going to put SF. If the scale factor is greater than 1, I'll have what type? Enlargement or reduction? Enlargement. So if your scale factor is bigger than 1, that is equal to an enlargement. If your scale factor is between 0 and 1, so it's between 0 and 1, you'll have a reduction. Is it possible to have a negative scale factor? Yes. If we have time, I'll explain what happens if you have a negative one. All right, so what's going to happen to my triangle here? Is it going to get bigger or smaller if I'm going to go dilation of 2? Bigger, all right, because the scale factor is bigger than 1. So I'm expecting a bigger triangle. Why am I expecting a bigger triangle? Here's what happens. Everyone right now, you have triangle ABC on your graph right now. When I dilate by 2, we are dilating, and I should have put this in the directions, but we are dilating around the origin right now. A has a certain, actually, let me go to C right now. How far is C from the origin? How far? 4 units, right? What we're going to do is, with a scale factor of 2, we're going to double that distance away from the origin. So it won't be 4 units away, it's going to be 8 units away, C prime. Right? And how do I get the coordinates of C prime? Well, this is a dilation. Dilation, you take your scale factor, and ready? You take your scale factor and multiply the x and the y of every coordinate by the scale factor. So for instance, C prime. C was 0, 4. So I take 0 and 4 and multiply it by the scale factor, which is 2. What are my new points? 0, 8. Oh, the distance doubled, didn't it? So now 1, 2, 3, 4, 5, 6, 7, 8. Here is C prime. That is what happens when you dilate a point. It gets closer, or in this case, further away from the origin. So I am doubling, all the points are going to double their distance away from the origin. All right, let's go to point B now. Point B was 4, 2. B prime can be found by taking 4, 2 and multiplying it by 2. So now B prime will be 8, 4. Everyone all right where I'm getting 8, 4? And watch where B prime is. It's double the distance away B was from the origin. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Here's B prime now. Notice I got further away from the origin. That's why the darn triangle got bigger, because every point is getting further away from the origin. And then finally, A prime. I'm going to take point A, 1, 2, multiply both coordinates by 2 and get 2, 4. 1, 2, 1, 2, 3, 4. Here's A prime. Okay? That is the reasoning why the triangle gets bigger, is because every point is getting further away from the origin. Questions there? Any questions at home? All right, now go to part B. Notice my scale factor now, a dilation of 1/2. 1/2. So what does that mean? Yes, the triangle is going to get smaller because what's happening to all the points now? They're getting closer to the origin now. Yes. Now my points are getting closer. I'll just go in the same order I did in part A. C prime, now multiply both coordinates by a half. So 0 times a half, it'll still be 0. 4 times a half, it'll still be 2. 0, 2. Notice C double prime is getting closer to the origin than C was. Okay, the points themselves aren't getting bigger or smaller. They're just moving closer or further away. So there's C prime. B prime, still multiply by a half. So that's going to be what? 2, 1. B double prime. I put my doubles there. And then A double prime, just do your best here graphing it, because I know it's going to end up being 1/2, 1. 1/2, 1 for A double prime. And there you go. That's why it got smaller. It's getting smaller because all the coordinates are getting closer to the origin. So that's how a dilation is performed. I multiply the coordinates by the scale factor. Any questions there, how a dilation actually works now?
I'm sorry, but I missed.
You're cut. I didn't hear the rest of your question there, Sophia. You cut out on me. Do you want to finish the rest of your question there, Sophia? I didn't hear the rest of it because it cut out.
Sorry, my internet cut out for
It's okay.
a minute. Did I miss any of the notes? Well, I'll try and get this on.
Okay. Any questions? I do want to just mention one thing before I move on to the next question. This whole multiplying by the scale factor, everybody, this whole multiplying by the scale factor to find your new points only works if you dilate around the origin. Okay, if I dilate around another point like I'm about to do in the next problem, I cannot multiply. The multiplying trick only works when you dilate around the origin only. All right, you can only multiply when you dilate around the origin. All right, well, what happens if I don't dilate around the origin? All right, in this case, I'm going to ask you to dilate a line for me. Okay, dilate a line. Ooh, how can you dilate a line? It doesn't get bigger or smaller. So I have line N, which is 3x plus 4y equals 20. And I'm asking everyone's help. Can you get me the equation of line P? And here's line P. It's a dilation of 1/3 of line N around 4, 2. Not the origin. So I can't, it's not dilated around the origin, so I can't just multiply everything by 1/3. All right, I can't do that. Only when I dilate around the origin. This isn't around the origin, it's around 4, 2. All right, I always like, I gave you guys a graph for a reason. I want to see what this line looks like. Can I get somebody's help putting this into y equals form so I can graph it? 3x plus 4y equals 20. Can I get your help putting it into y equals form so I can graph this sucker? All right, let's talk to 4 here first. No, I'm not going to do that. How about I go to 25 instead? Sabrina, can I get your help putting that in the y equals form? Well, just let everyone know what you're doing first before you get there. What do you want to do first to get it into y equals form? Okay, so I get 4y equals negative 3x plus 20. Go ahead, keep talking to me there, Sabrina. Yep, divide each side by 4, so I get y equals negative 3/4 x plus 5. Everyone all right? Okay, let's throw this on the graph right now. 5 is my y-intercept. 1, 2, 3, 4, 5. Down 3, 1, 2, 3 over 4. 1, 2, 3, 4. Down 1, 2, 3 over 1, 2, 3, 4. Let's graph it. Okay. So how do I dilate this line? Because it's certainly not getting smaller. Right? Lines don't get smaller or bigger. They just go on forever. Okay, wait a second. We're going to dilate it around 4,2. Hey guys, take a peek for me. Take a look at the point we're going to dilate it around. 4,2. Anybody want to tell me anything about 4,2 in this case? Oh, where is it located? It's on the line, isn't it? All right, stay with me here. Stay with me. Now that you know what actually happens to a point when I dilate, if I'm going to dilate by a scale factor of 1/3, are all the points going to get closer or further away from 4,2? Closer. All right, ready? Let's try this and see where we end up with this. Let me take my y-intercept here, and let me get closer to 4,2. Where's that point still going to be? It's still going to be somewhere on the line, isn't it? If I take my y-intercept and get 1/3 of the way closer to 4,2, I don't know exactly where it's going to be, but I know it's going to land on the line, isn't it? All right, let me take another rando point here. Let me take this point down here that I graphed. If I get 1/3 of the way closer to 4,2, where's that point going to land? Still somewhere on the line. I take any point on this line and make it 1/3 of the way closer. Where's it still going to land? What's my image going to be? The same line. Does everyone see that? When I dilate around a point that's already on the line, it's going to stay the same line. I am never going to get a point off the line anywhere. Kyla, go.
Would the slope still change, or would the slope change because the points are close together? It does not matter.
It's the same line, right? The slope's going to be exactly the same. Same with the y-intercept. It's not going to change. Radhika.
How would you do it if the point wasn't at 4,2?
That's,
It wasn't on the line.
you're going to have to think about that tonight.
Okay.
That's a challenge one tonight on the homework. Okay? Tonight on the homework, you are going to get one that's not on the line and not the origin. So you guys will think about that a little tonight. All right? I'm going to make you think a little. So here, line P is still going to be 3x plus 4y equals 20. Everyone at home, see why it stays the same line. Your center of dilation's on the line, so every point's just getting a little bit closer, but remaining on the line. Okay, I will never get a point off the line. Questions? All right, let's go a little something slightly different. Let's still dilate a line, but now around the origin. Okay, let's dilate a line again, but now it's on the origin. And that's a 3, by the way. Sorry, I got cut off somehow in your notes. That's a 3. So I'm dilating it by a scale factor of 3/4. All right, well, what's this line look like first, right, guys? Let's see, down 1, 2, 3, -4 is my y-intercept. I can go up 3 over 2. Up 1, 2, 3 over 2. So there's my line that I'm going to dilate. Around the origin. Is the origin on this line? No, so it's not going to stay the same line like last problem. The origin's not on there, so how am I going to do this one? Well, we remember from our triangle example in number 2, if you ever dilate around the origin, what can I do to find new points? I could take my scale factor and multiply the points by the scale factor, 3/4. All right, let's see if I need to go through all that work, though. I want you guys to think about this. I'm going to move 3/4 closer to the origin. That's what the scale factor is telling me, 3/4. Every point's going to get 3/4 closer to the origin. Anybody got a prediction about the slope of this line and my dilated line? All points are just going to move 3/4 closer. Maeve, what do you think about the slope? It's going to stay the same. When I dilate, any dilation, no matter what point I dilate around, slope will always stay the same. Slope, dilations do not change the slope. But one thing that will change is what? When I write my equation, the slope will stay the same, but what will change? My y-intercept will change. Okay, my y-intercept, it will definitely move here. So my y-intercept is different. And how can I find my y-intercept? Well, what's my y-intercept now? 0, -4. Everyone, that's my y-intercept now. And since I dilate around the origin, what can I do with my y-intercept and my scale factor of 3/4? Multiply, multiply, multiply. All right, because I am dilating around the origin, to find the new point, I can multiply my point by the scale factor. So 0 times 3/4 will stay 0. I just got to figure out -4 times 3/4. And that'll end up being -3. So there's your new y-intercept, 0, -3. So that put the two together, the slope stayed the same, and my y-intercept is -3, leads me to choice number 4. Whew. Questions, comments from you guys? Dilating, okay, so far we've talked about dilating around the origin. I can multiply by the scale factor. Dilate around a point that's already on the line, it stays the same line. So knowing those two, I want you guys to work on numbers 3 and 4 right now. Okay, work on number 3 and 4, knowing all that information we've talked about. So you see number 3, you're going to dilate around 0,6, so a point that's not the origin. And the same thing on number 4. Both questions, you are dilating around a point that's not the origin. When you guys are doing number 3, hopefully you find that, hey, wait a second. 0,6 is on the line I'm trying to reflect. -3x plus 6. It's its y-intercept. So if the point, the center of dilation is on your line, the line will not move anywhere. It'll still stay the same line. So I'm hoping for number 3, you guys got choice 2. It ends up being the same line. And I know most of you guys are working on Aaliyah here. 4x plus 3y equals 24. You're doing the same steps as our first problem we did like this, getting the y by itself. Negative 4/3 x plus 8. And then as you graph it, what do you notice about 3, 4, the point you're dilating around? It's on the line, isn't it? It's on the line. All right, so Aaliyah, I am sorry there. Hate to break it to you, but that's not going to be the equation of the dilated line. Anybody see what she actually did? She didn't dilate around 3, 4. Where'd she dilate around? The origin, right? She kept the slope the same. She took 8, multiplied it by her scale factor of 2, and that's where she got her 16 from. Silly Aaliyah. That is only for if you dilate around the origin. So she is incorrect. And then I will leave it to you guys to explain why. She dilated around the origin instead of 3, 4. 3, 4's on the line. So therefore it stays the same. Whatever your explanation happens to be why she's incorrect. All right, questions there? I just want to keep moving just to make sure I get through everything here. I got 12 minutes. Any questions from you guys? All right, so we got 2 more. I'm going to get off this whole dilated of a line problems I'm on, and I want to go to our good old friend distance now. Yay, distance. So there's line segment AB. You guys see the coordinates? I don't care about AB. I want to know what's the length of A prime, B prime if I dilate AB by 1/2. I want to dilate around the origin as well. That's key, around the origin. So you know what AB are, but I want to know the length of A prime, B prime. And it's a dilation of 1/2 of AB. So I want to get your thoughts here, how I can start approaching this, because there's actually 2 different ways I could go with this. I can approach it 2 different ways. Radhika, you want to give me one way you're thinking?
If you take A and B and put it through a dilation of 1/2.
Okay, so you're saying do the dilation first.
Yeah.
Okay, so what Radhika's saying is, hey, I'm centered at the origin, so find A prime, B prime first, and then do what to find the length?
Find the distance.
And then distance formula. Yep. That's one way to approach it, is find A prime and B prime first, and then use the distance formula on those 2. Did anybody have another method? Because you actually, Sean, go ahead.
You do the distance formula first, then divide it by 2.
There you go. Second way I could approach this is distance of AB by using the distance formula, and then multiply by 1/2. Either way will get you there, so go ahead. Either way will get you there.
Wait, if you do it the second way, would you just take the answer and then
Multiply it by 1/2, yep. Cut it in half. Okay, hopefully you guys are finding either method, the distance of A prime, B prime, 2.5 units. Okay, the distance of AB turned out to be the square root. Yep.
I think I did something wrong in that case because I got square root of 8.
Which method did you use?
The first one.
Okay, so you should have said A prime was, let's see, 1 and let's see, 1.5. B prime should have been 2.5, negative 0.5. That's what I got for A prime and B prime. Yes, no?
I mean, I did some. I put down 1/2 for the first coordinate of A instead of 1, but even so, I don't know if.
I'm not too sure what you're asking here, Sophia. I got to multiply A and B by 1/2 because that's the scale factor. So I took point A, multiplied it by 1/2, and got 1, 1.5. I took B.
No, it's fine. I think I did some wrong calculation.
Okay, and then I take those 2 points and plug them into my distance formula. Other questions, comments, concerns before I get on to the last one?
So then you get 1.5 squared.
I'm not too sure. It should be distance equals 2.5 minus 1 all squared plus negative 0.5 minus 1.5 all squared. So you end up with 1.5 squared plus, what's that, negative 2 all squared. So whatever 1.5 squared is plus 4, add them together and then take the square root, you should get 2.5.
Yeah, it is 2.5.
Mm-hmm. All right. All right, last one. Why aren't dilations rigid motions?
The side lengths don't stay the same.
Right? In a rigid motion, side lengths and angle measurements are preserved, and in a dilation, side lengths are not preserved. But what is preserved? Angle measure is always preserved when I do a dilation, meaning triangles won't be congruent, but since angles stay the same, they can be similar. Because anybody remember the main way of proving triangles similar back in that unit? Angle, angle. All right, so if the angle measure is preserved, the triangles would still be similar, which is almost the case, which is almost the type of proof I'm going to ask you here to end class. I got triangle ABC, and you guys can see the A prime, B prime, C prime version on your paper. It says describe the transformation performed, which I think we can all agree this is a dilation, right? We got a little bigger. But you know a dilation isn't good enough for me, right? What do you need to tell me as well? It's a dilation, and you also have to tell me what do you think I'm going to be looking for? The scale factor, right? Since it got bigger, what you should know at least one thing about your scale factor: bigger than 1 or in between 0 and 1? Big, definitely bigger than 1. How do I determine what the scale factor is? Any idea? There's a couple ways I could do this. How can I determine, Rudika, what the scale factor is?
You could find the point of A prime and the point of A, and then figure out like how much is like.
There you go. Find 2 points, a pre-image of an image. That's one way. You got another way, Kyle? Yeah.
Oh, no, I have a
Oh,
question.
sorry.
Are we assuming that it's around the origin?
You can, yes.
Okay.
Yep. We should have put that in there. You are correct. Yep. Anybody, another way? Are you guys just going to do the points then? You could also compare 2 sides too. That's the other way to do it. Because you can count BC and B prime, C prime, and see what ratio they're in, and make sure it's bigger than 1. So let's see if you can find the scale factor here. Anybody finding the scale factor here? 5 over, or 2.5? Everyone getting 2.5 or 5 halves? Yep, you make sure you got 2.5. Make sure it's not the smaller version because it's got to be bigger than 1. So a dilation with a scale factor of 2.5 or 5 halves if you want to write it as a fraction. And now it says explain why the two triangles are similar. We're going to write this just like we did our proofs with rigid motions, except now I'm going to say dilations preserve what? Angle measure. Dilations preserve angle measure. Thus, in conclusion, triangle A prime, B prime, C prime, similar to triangle ABC. Because remember, one method was angle, angle, and if angle measure is preserved, the angles are congruent. All right, guys. Do not listen before we sign off. Do not give up. There's one problem tonight where you're going to dilate around a point that's not the origin and not on the line. So I'm interested to see what you're going to do there. Don't give up. All right, I'll see you guys tomorrow so we can talk about the test. Have a good night.
I know we're discussing tomorrow on the day after. What? I don't even know. Yeah, I know.